Buhler from Courant, and the title of the talk is Internal Waves and Wave-Induced Mean Flows in the Ocean.
Thank you very much, Andre. Thank you very much for organizing the conference, and it's a pleasure to be here. I've been here at IMPA before, and it's always nice to see. I did switch it on, honest. It's on? Okay, I tried my best. So as I said, it's very nice being here, and also it's always great to see the tiny little differences that arise in every place. Like I noticed you have ashtrays in your conference seats, so is that correct? Yes, probably not used very much anymore.
Decorative now, I think.
Oh, it's just decorative now. Okay, well. So I want to give a talk about internal waves in the ocean. And it's joint work with Miranda Holmes-Chaffon, who was a PhD student who graduated last year, so that's one half of the work. That work is completed and is in press now. And the second part of work is with Nicolas Guizois, who is a postdoc who started at the Courant Institute in January. So this is work in progress. That will be the second half of the work that I present. So the topic of it all is linked, actually. I mean, it's a story about ocean waves that are linked to tidal frequencies, so in that sense it's a continuation of Esteban's talk. But the story actually starts not on Earth, but on the moon. So here is the man on the moon, but it's not so important that the man is on the moon. It's important that they actually left something behind, and they left behind a mirror that allows you to very accurately measure the distance between the moon and the Earth. And to me, apart from the Teflon pan, that's the only tangible outcome of manned spaceflight, is that they put this mirror on the moon, because the situation is that the moon's orbit is not constant. In fact, the moon gains angular momentum and energy all the time from the Earth system, and that makes it recede at a very small rate. And with this mirror, it is possible to measure this rate of recession very accurately, and it's 3.8 centimeters per year. Now, the beauty of that result is that you can now go back with your favorite undergraduate textbook in mechanics and work out from this number what is the energy dissipation in the ocean. And the reason for that is because the moon gains angular momentum and energy from the Earth. The angular momentum is precisely lost by the Earth's rotation, so the Earth is spinning down slightly because of this. But you can also compute the energy changes in the Earth system, and by the beauty of momentum conservation, the energy change in the Earth system is actually bigger than the energy gained by the moon going to a higher orbit. So whatever the Earth loses in excess of that has to go into dissipation, and the belief is it's not happening in the solid Earth, it's happening in the fluid envelope, mostly in the ocean. So by knowing this number now and doing this beautiful little calculation, which I recommend if you have stranded in an airport somewhere, it's a good thing to do, you can actually work out that there's 3.2 terawatts, 10 to the 12 watts, going on of dissipation in the ocean globally. It was originally believed that most of this is happening in very shallow seas in the Irish Strait. Lighthill had a theory about this, but that's not what's believed anymore. Believed now is that a large fraction of these 3 terawatts is actually happening in the ocean interior. And that got people very excited because there's a great absence, a dearth of mechanisms to have turbulent. I mean, this dissipation manifests itself in turbulent dissipation. It's really the dissipation that happens in the inside of turbulent activity, and there is a difficulty to actually have turbulent dissipation in the ocean, in the interior of the ocean. So this is an exciting development for the ocean community, because this is sorely needed to understand or to be able to put together a picture of the ocean circulation. So let me try to explain a little bit what the problem is in the ocean circulation. So here's a picture of the overturning circulation, so the idea that the water masses in the ocean, the warm ones, go along the surface and then they sink in very cold spots, sink down to the floor of the ocean. Then they eventually have to return. An epic journey that takes hundreds, if not thousands of years for water particles. But the problem is, in order to have this kind of overturning motion, you need to have agencies that allow water masses to kind of cross through each other. So if we go to a little cross-section here of that's indicated as green here, then this picture, the next picture, shows what the problem is. So here is a cross-section, so this is latitude going up north through this little green area, and this is where the previous picture would show there should be some rising motion if this conveyor belt image was true, and indicated here are stratification surfaces. So these are lines of essentially constant density, which, if there was only advection by these red arrows, these lines would deform. They would be dragged away with the fluid until they're completely washed out. Now, this is clearly not happening, so there can't be just advection. In fact, it's believed that this system is an advective diffusive control, so there must be an agency that provides the diffusion that actually allows these stratification surfaces to stay in place. And the dissipation provided by the lunar recession is actually the main agent that will provide that diffusion. So it's a very interesting situation. I should mention that it's not such a local picture. Particles can relatively easily travel along the horizontal, along these stratification surfaces, and some of them can then connect to the open ocean surface at these latitudes, where they can easily diffuse across these density lines. So there's also an alternative view of this, that in the interior very little is happening. Eventually a particle makes it after 1,000 years, makes it up here, and then it gets mixed across and can go down again. So you can also think about this as being a more complicated picture with a lot of horizontal advection, localized diffusion, and then bringing the water back down at depth. So there's a lot of story going on to understand the ocean stratification, the basic structure of the ocean, in the presence of an overturning circulation.
So is your idea that the diffusion actually carries lighter particles back down to keep the constant density lines in place?
So the original, the theory that was proposed in the 60s that makes this picture most clear is saying there's just cold water dropping to the ocean floor every now and then in kind of a narrow convective needle, and then there's more or less global upwelling everywhere. And to maintain a stratification like this against this global upwelling, you have to diffuse the heat down. So that's the simplest one-dimensional picture that was proposed in the 60s.
It's very hard to push light fluid down.
Indeed. But then in the ocean, sort of, do almost anything in the ocean tends to be hard. And the timescales that are involved, I can say it again. So to start an ocean model from rest, if you like, with some arbitrary stratification and then allow it to spin up to a state that looks like what it currently is observed requires thousands of years of integration time. So the timescales that are involved here are extremely long. The motions are involved here. The vertical motions are sort of millimeters per, I even forgot what it is, but it's very small. It's millimeters per second. So it's always a tender balance between some fairly small terms. Okay, so the other aspect of that picture I wanted to highlight is that what does it have to do with waves? Well, there's this Brazil basin data. In the 90s, the Woods Hole Oceanographic Institution managed to produce an instrument, looks a bit like a torpedo that would fall down vertically, and managed for the first time ever to measure direct turbulent dissipation in the ocean at depth. And that measurement campaign was done along here, and this is the data that came out of this. So that's the plot that launched 1,000 ships, because you could suddenly see that these are the diffusivities. You're converting the measured turbulent activity as a simple formula into an effective diffusivity for the vertical, and you can see it's mostly purple. And this is not my color scheme, now the purple is from their paper. So it's very, very low, so significantly lower than 10 to the minus 4, and then you have these very, very increased regions over the rough topography. And this is not a boundary layer effect. These distances are easily 500 or 1,000 meters high. So something must propagate the roughness of the topography up through the water column and then create this turbulence there. And the belief is that this is all due to internal waves that come off this topography, propagate in the vertical, and then break. Right? So the whole story, the whole question is, how does the tide, that the original tide that comes from the moon, the barotropic tide, the tide that Laplace studied, where the entire fluid envelope just rocks back and forth, how is that connected over so many steps with the actual then turbulent dissipation and diffusion that takes place on scales of tens or hundreds of meters in the ocean? So that's the big story. So here's a schematic of the energy cascade that we can kind of visualize or conceptualize this problem. So there's the barotropic tide, Laplace's tide, that interacts with topography, and a process that an oceanographer is called tidal conversion, then creates internal waves essentially of the same frequency. Those are at fairly low modes still, so the barotropic tide is uniform in the vertical. These first-generation internal tides have fairly low modes in the vertical. There's a scale cascade then, with a variety of mechanisms, almost all of them speculative, that leads to internal tides now of higher modes, and then eventually instability of those tides break down into turbulence and mixing, and then an interaction with the actual overturning large-scale circulation. So the two pink arrows that are highlighted here are the two projects I want to talk about. So there's a first project with Miranda Holmes was on this aspect here. What is a scale cascade? What are the possible mechanisms? And the second one is then what are the non-interactions with the mean flow that come out of this? Okay, and please do feel free to interrupt and ask questions. I'm aware that it's a very heterogeneous audience. So the governing equations for this kind of system in the ocean, it's a very good approximation to treat it as a Boussinesq fluid. So it's a rotating Boussinesq equations. In these kind of local models that I'm going to talk about, we use an F-plane, so the Coriolis parameter that in Esteban's talk, it was crucial that it varied with latitude. We treat it as a constant here because our domain of interest is only a few thousand kilometers. There's a three-dimensional velocity. There's the Boussinesq equations. It's a Coriolis term, a pressure gradient. It's incompressible. And then there's this buoyancy disturbance. The buoyancy field, which itself satisfies this equation. And what that really expresses is that there are stratification surfaces on which the quantity b plus n squared z is constant, and that is a material surface, so it just gets dragged around with the fluid. And then there's a tidal potential, which captures the time-dependent potential due to the moon. And if you treat this in full generality, this will be dependent on both space and time. In a local model, this gradient is essentially uniform, and it just depends on time, at which point we can actually redefine it by we can eliminate it by going into a frame of reference that moves with the fluid that now gently rocks back and forth with the barotropic tide. And then this potential then precisely provides the inertial forces necessary to make everything work, so you can get rid of this term by allowing yourself to swim along with the ocean. And then the topography underneath you moves back and forth. Right? Okay, and we have no normal flow conditions at the ocean top and bottom. So that's the governing equation system. For the first part, I'm going to talk about the linear equations that belong to this. So I assume that the velocity is a small parameter times some field, where the amplitude is very small. And that leads then quickly to a simple equation with constant coefficients for, say, the vertical velocity, horizontal derivatives, vertical derivatives, and both this parameter for the stratification, n squared, and for the Coriolis force. So if we're interested in tidal motions, when we know the period of the motion, so we assume it's time periodic with that period, so we can reduce everything to a single complex valued amplitude field that depends on the three spatial coordinates. And if we put this in here, we get a simple equation which describes the spatial structure of these time periodic motions. And what's important to notice here is that in the regime we're interested in, this parameter mu squared is positive, and that means this equation that describes the spatial structure is actually a hyperbolic equation. So it's unlike an acoustic problem where that equation would be an elliptic equation. This is a hyperbolic equation. So that comes up in a variety of ways and makes the linear problem itself actually interesting and non-trivial, unlike the corresponding problem in acoustics. Okay, so the parameter value mu here, just for indication for the lunar semidiurnal tide at Hawaii, the M2 tide has a value of just under 1/10. And typically oceanographers like to study things that happen in Hawaii. It's nice to go on a cruise there rather than going to the Southern Ocean. Okay, so this is what this field looks like. So this has been computed. This is just solving linear equations with no normal flow conditions at the top here. There's a little Gaussian mountain that will rock back and forth. And then the boundary conditions are radiation boundary conditions into an unbounded domain left and right. And this particular solution has been computed using a Green's function for this unbounded channel. And what's plotted here is in the colors is the vertical velocity, and the arrows are the actual fluid velocity for the linear equation. So if this runs, you can see this mountain rocking back and forth, and then coming off that are these internal waves. And you can see immediately that this is very unlike an acoustic problem because the wave energy remains tightly focused in these conical regions, or here just lines in this two-dimensional cross-section, because of the hyperbolic nature of this equation. And the equation is almost like a plane wave along these lines, that there's very little gradient, and then the flow has to turn around up and down. That's the main seat of the nonlinearity. So the barotropic tide rocks all the fluid particles back and forth about 150 meters. This is greatly exaggerated in this plot, so to make this very visible what this topography is doing. Okay. So now this is the system of interest. What's then typically done in oceanography is consider the flux of energy. So energy is defined in the usual way for the perturbed fields. And then the energy flux is the pressure times the velocity. And then if you do this, then you get, so the colors are still the same as the vertical velocity, but the arrows are now this energy flux. You can see that now always points away from the topography. You can put a control volume there. and measure the time-integrated energy flux out of this. And when people do this, they come up with approximations for the total ocean of a conversion rate of about 1.5 terawatts. So if you go back to the moon picture, 3.8 are available, and roughly something of the order of half of that seems to be directly converted into these internal motions. And therefore, that's the beginning of the cascade. I mean, these modes won't dissipate, but once they're there, they can become part of the game that in the end leads to the diffusion that will lubricate the entire ocean circulation. So this is the kind of number that is typically estimated for the global ocean. Here's some oceanographers did a 2-layer model, so that is less, doesn't have continuous stratification, but allows to have at least one baroclinic tide in it. And they studied the temporal spreading of the tides through the entire ocean. So there is, if we find Hawaii somewhere there, then you can see that that's where the sort of tides start. At day 0, they start with no tides, and then it spreads through the entire ocean. So it's this complete network, it's this huge amount of tidal energy that comes from this baroclinic conversion process. Okay, so that brings me to the first of the two projects. What we wanted to do is we wanted to see one of the mechanisms that can reduce the scale of these first-generation internal tides is by scattering them over the rough topography of the ocean subsequent to their generation. So it's not the generation by the topography, it's in the subsequent propagation and continual interaction with the topography that leads to a scattering and reduce their scale. And we studied that in 2 dimensions. And so this is a paper that's now in press in JFM and should appear in July. And we wanted to do this for realistic-looking random topography in the ocean. So the setup is now, it's the same channel as before. Here we use the stream function for the flow. It's just in 2 dimensions. So there's a wave already coming in from the left. And then there's some topography here. So this topography is compact. And then there's some scattered backwards and some scattered forwards. And what we try to work out is how the energy flux in the primary wave decays as it rolls along this topography. So the equation is as before, the linear equation. You already saw that. Stream function rotation is included. And yes, the radiation conditions, everything is as before. But we are solving this now not with the Green's function approach, but with the method of characteristics, because it turns out that after you scale the spatial equations, it just reduces to the one-dimensional wave equation, which you can solve by assuming that the solution consists of 2 functions, one of the x plus z variables and one of the x minus z variables. And then because of the homogeneous boundary condition at the top, you can reduce it to one function. So you just need to find one function of one variable, and then you have solved the entire problem. So to do this, well, now what happens, of course, is that this is an ill-posed problem. So to try to work out how this function depends on the boundary data is essentially an ill-posed problem because of the hyperbolic nature of the equation. So this was apparently first pointed out by Sobolev in the sort of nascent Soviet space program about research in rotating fuel tanks for rockets, and it gets rediscovered roughly every 30 years. So every 30 years there's a paper proclaiming that this is fantastically new, and it is new. It is each time you discover it, it's new. But it's every 30 years, so we're probably going to shorten this cycle now because so many people have worked on this. So the idea is that this function f that you really try to find, you follow a characteristic down, and then the reflection rules work out that the same value of this function is then replicated at this point x1. So if you know the function here, you also know it over there, and you try to piece together what the function is globally, and then you know the global solution. So the actual geometry is that if the topography were just flat, you would get just a regular 2 pi distance between these 2 points where the function is to agree. If the topography has a dip there, it will take longer for them to come up, so that will delay its arrival. If the topography is up there, it will shorten its arrival, and that will give you a non-uniform kind of spacing for the arrivals of these characteristics. And then once you've put together a whole map of how the characteristics travel from left to right, then you need to actually specify the solution on this, and for that there's this is Miranda's slide. This is the naive solution, which is what I said it would be the solution. It's the supervisor's idea, that you just put in the wave from the left, because what else could you put in? And then you get the result by following the characteristics along. And that gives you the wrong answer, because the radiation condition isn't satisfied on the right then. So you have to allow for the incoming wave and also the reflected wave and so on. And then you have to solve a spectral problem left and right at the end, once you find out the characteristics to actually get the right answer. And it's essentially to do this right. You get completely the wrong answer by this. So the only excuse is that I'm not the only one who made this mistake. The list of people who got that wrong is long and distinguished, but I won't go into it. Okay, so when you do this, this is what happens. So here's the incoming wave, and this is if you just pick a random wave number for like 10 or so oscillations. Here it's flat here, flat there, and just have this. And you can see the wave is a little bit disturbed, but more or less rolls along easily and can propagate over long distances. This drastically changes if you pick a wave number for these topography undulations that actually matches the kind of scale of the vertical modes, in which case you have now a resonant wave number, and you get this very rapid transformation of this blobby shape into these sharply focused propagations along the characteristics that come off a particular location of these topography features. And that's very robust. The wave number 1 is special, as in many wave problems, there is no back reflection. If you go to wave number 2, you get the same focusing, but you also get a significant amount of back reflection of waves, so the waves are coming out left and right. Notice that the scale cascade is really very dramatic. So if this wave is stable, then the shear has greatly, greatly enhanced over there. And so it quickly gets to the point where the wave can actually participate in instability and produce turbulence. So there was a summer project at the GFD summer school a couple of years ago where we looked at this just for a very simple topography. And there, for the wave 1 modes, it was very obvious that because a characteristic that hits at 0 would return at 0 as the topography replicates itself, and if it starts slightly above or below, it would either wander away from the fixed point or go back to the fixed point, so there's a stable and an unstable fixed point. And it was very easy to actually convince ourselves that that is the answer for these simple things, that this is a focusing of all the characteristics into a stable fixed point of this periodically repeating topography. It's really the neighboring characteristics coming closer and closer together. So the question was, well, how does this focusing persist for irregular topography? So we put down a random topography, which is just a Gaussian random function. So what that means in practice is that you pick a Fourier series where all the coefficients are drawn from normal distributions and independent of each other, and you can specify the variance depending on the wave number. And then I still think it's one of the most amazing results in mathematics is that then the random function you generate like so is then a Gaussian random function in the sense that not only is its distribution at a fixed point a Gaussian distribution, but it's a distribution at any n points you care to pick, independent of what the number n is. It's a multivariate Gaussian distribution. So even if you observe this function at 700 points, there will be a 700 variate Gaussian distribution with this simple recipe of generating this function. There's no indication that the ocean seafloor is Gaussian, right? It's what you, of course, use to have the simplest model. Okay, this is just, we are not interested in rough topography, so we actually chose a covariant structure that gives you a smooth sample functions. So this is a typical plot of our random topography. Okay, and if you do it over random topography, well, obviously this will persist. And the question is now, can you draw conclusions about the sort of the expected decay range of this wave given the spectrum of your topography? So to do this, well, it's a focusing of nearby rays. So the simplest model is to sort of think about a random walk and the foot points of these waves, and there are two neighboring rays, and there's the same topography that generates this random walk, but they're at slightly shifted positions, and then their difference solves approximately a simplified stochastic differential equation, which for small, when they get close together, which we can solve. And it gives you this answer. And I'm only mentioning this because some people have interests in financial mathematics. So this is a model for geometric Brownian motion. So it's an interest rate model where the interest rate is extremely random. And then the separation or the wealth of your retirement portfolio goes to 0 with 100% probability as time is long enough. So necessarily these characteristics will focus together and fuse and then never separate again, if you like, in this kind of model. So we tried a few other things, but this seemed to be the most robust model to think about it. And this is the expected value of the energy flux over about 100 realizations. And you can see there's essentially an exponential decay with the number of bounces over the topography. This is not true for a single realization, but it's true for the expected value. And we were able to find out what is the decay rate with the number of bounces. And it gives you this very nice formula, which is just a sum over all the integers that fit this recipe multiplied by k. And it's very easy to sort of speculate about this formula. And we made a really big effort to derive it. One of the weeks we followed the theory of Papanicolaou and Marpin. But unfortunately, we always managed to derive this formula, but never with a 1 in front. So we had various versions that had a half or something to do with pi, but we never managed to get it actually with the right coefficient. So you can, depending on whether you're an optimist or a pessimist, that's significant or not. I don't know. Miranda was a very good student, and she worked very hard. We worked together. But we didn't get to a derivation where we actually got this cleanly. But this is very clearly the right answer because it fits the numerics beautifully. It is perfect. But the derivation, we could never match the coefficient. So in the paper, we then went on to actually apply this to the ocean model spectra that are being used, and that gives you decay rates that you can sort of then speculate about in the ocean, but I don't want to talk about that here. So that's the story. That's the story for that problem. So let me move on then to the second problem, where we go back now to the end of the cascade. We now imagine that the waves are actually dissipating. There has been some mechanism that made them small scale enough. Now they can dissipate and break. And we know from a lot of work in fluid dynamics of the atmosphere that internal waves, when they dissipate, can drive very important mean flows, be it the quasi-biennial oscillation or the entire sort of overturning circulation in the atmosphere is wave-driven. And then as a basic fact of wave-mean interaction theory, it comes up over and over again, that the mean flow feels such waves not where they're generated, but where they're dissipated. So we are trying to apply the kind of theory that has been developed in the atmosphere over the years to this ocean internal tides. If you're interested in this topic, then there's now a book you can buy on this topic. As well, it was subtle enough, right? It's not an unsubtle arrangement. So let me show you what is involved in this. So the starting point is what Reynolds did for turbulence flow, which is the Eulerian interaction idea, where you split the velocity field, say, into the linear perturbations or any perturbations and the mean flow here averaged over the phase of the waves, such that when the perturbation is averaged, it gives you 0. And then you can work out what are the equations now governing the mean flow. And at leading order, if the waves are order A and A is a small number, then the mean flow will be order A squared. And so if you collect terms at that order, you get this equation for the mean flow. So on the left, I still have an incompressible flow. I have a flow that's governed by the same terms as before, except there are now all these Reynolds stresses on the right-hand side. And similarly for the buoyancy equation, there are all these buoyancy fluxes on the right-hand side. This is extremely uninviting, even at leading order. And in fact, to my knowledge, in the kind of situations that we're interested in, which are not very symmetric in the spatial variables, no one has ever made head or tails out of these equations. So in the sense that you could sort of point to these terms and say they will be 0 under certain situations or something. That just doesn't work. So there's also complication at moving boundaries, that the normal component of the mean flow doesn't actually vanish there because of Stokes drift corrections. So it's very hard to draw any conclusions from this. So the theory that we used instead is Lagrangian averaging, which is the idea is that instead of averaging at a fixed point in space, you try to stick to a particle and time average or phase average as you follow the particle. So you conceptualize the motion of particles having a slow drift, which moves with the Lagrangian mean flow, and then there's a rapidly fluctuating part, which is given by this field psi, which links the mean position of a particle x to the actual position as it fluctuates, which is then x plus psi. So the mean and actual trajectories are related by that this is the actual position of a fluid particle whose mean position is x. So when you do this, you can now average the equations, but not at the Eulerian, at a fixed point, but at a fixed particle. And that allows you to retain a lot of the Lagrangian information. For instance, these stratification surfaces are material surfaces, and they retain now their character of being material surfaces in the Lagrangian viewpoint. So now the Lagrangian wave interactions, you get, for instance, the buoyancy now satisfies the same equation as before. It's still materially advected with this Lagrangian mean flow. Unfortunately, the flow is now compressible. So there's a little term here. I don't want to go in there why that is there, but the flow, even though the original flow is incompressible, this flow is now looks as if it's compressible a little bit. And the equation for the vorticity is particularly easy. You have the usual vorticity terms. There's the vorticity time derivative, divergence effect, tilting of background vorticity, and then this baroclinic term due to the stratification. And on the right-hand side, you have the time derivative of what's called the pseudo-momentum, which is defined in terms of properties of the wave. So here's the wave disturbance field, here's the displacement field, and displacement field and the wave velocity are linked by this time derivative. For a plane wave, P is just the wave number vector divided by the intrinsic frequency times the energy density. In general, that isn't true, but this is the general definition. So now you have this equation. This is much easier to analyze. I mean, you might not think it's much easier, but let me give you an example. Suppose the wave field is steady, then this term is 0 because it's a time derivative. This term is 0 because this term is 0. And this term is 0 because it's also a time derivative. Then everything has disappeared. We have suddenly proven a result that is impossible to prove in the Eulerian framework, that a steady wave field under these assumptions has no impact on the Lagrangian mean flow. It does not lead to anything. All the forcing terms drop out. So the Lagrangian mean flow does not react to this steady wave field. So what we need to do in order to get anything is exactly what we have learned from the atmospheric dynamics case, which is we need to add dissipation. So this is the magic result. The steady waves do not force the mean flow, and this is impossible to derive in the Eulerian representation. Okay, so now we add wave dissipation. Here our model is really crude. We simply add a linear damping term to the perturbation equation for the buoyancy. So instead of having 0 here, now the temperature signal is slightly damped. And that is not a good model for any physical process, but it is a very simple model for the decay of waves by some process that doesn't mess up momentum conservation or anything like that. So if we do this, then the equations for the mean flow, there's still nothing here because we only apply this damping to the perturbation equation. It's still for a steady wave field. There's no divergence. And this equation, there's now a new term, which is the curl of some effective mean force. And that effective mean force is 0 if alpha is 0. Alpha is a damping parameter. And otherwise, it has this particular form that you can express in terms of the complex valued vertical velocity. So it's the imaginary part of this combination times some other stuff there. So this is what we worked out. But it basically allows you now, well, if you have a wave field, you can diagnose this effective force field, and you then get the forcing of the mean flow in the vorticity form. So you can work.
What happens if alpha goes to 0?
If alpha goes to...
This looks like a delta function there.
That's true, but omega is fixed here. So omega is the fixed frequency of the primary waves you start with. So when alpha goes to 0, this denominator remains finite at omega squared. So we're not interested in the case where omega can go to 0. So if alpha goes to 0, the answer is f just goes to 0. Nothing happens. So what does it look like for exactly the wave problem I showed you earlier with the topography that wobbles back and forth? We computed what this force field looks like. So this effective force is the arrows. You can't see them too well. And then the curl of that, which actually enters the vorticity equation, is given in red and blue. So the red is clockwise curl. So this is a circulation that's trying to spin up like clockwise. This one spins up counterclockwise. And you can see that kind of main driving of the mean flow is localized near where the waves are generated here. They bang around. And then most of what happens further out is at these nonlinear, the regions where nonlinearity is quite strong, where the waves have to turn from going up to going down, and so on and so forth. So what's the actual mean flow response to this? Well, we can work that out as well. So in two dimensions, so we just take a horizontal and vertical slice to the problem, you can actually reach a steady state mean flow where the horizontal velocity in the x direction and the vertical velocity are both 0, and then the meridional velocity, the in and out of plane velocity, and the buoyancy field are non-zero to balance this force curl that tries to spin up fluid particles. So you get a balance between that and the tilt of the isotropes and the tilting of the planetary vorticity. And you can actually get a unique answer if you consider this quantity, which is really the potential vorticity. And if you take the time derivative of this and use the equations that I showed before, you find it out that the time derivative is 0, so it retains its original value. If you set that to 0, you can solve these two equations with some kind of stream function, and you get this equation that tells you how to work out the adjusted state. So the mean flow does adjust to the presence of the waves, even the dissipating waves, but it doesn't lead to any runaway acceleration. But this is really a kind of a result that's not robust. It's really just a two-dimensional result, because in 3 dimensions this won't happen. So in 3 dimensions, that's really the case we're interesting. And there, you can define the potential vorticity of this flow as such as the curl of the difference between the Lagrangian mean flow and the pseudo-momentum field. And then there's this term that has to do with the background stratification. And if you take the time derivative of this quantity, then without waves dissipation, the time derivative of this quantity will be 0. But with the wave dissipation, the time derivative of this quantity is in fact exactly the vertical component of the curl of your effective force field. And that means, because the effective force field is time independent, that in this simplest regular perturbation approach, the potential vorticity just grows unbounded in time. I don't know why it says 333. There's no... Oh, this is from the page in the book. Okay. Thought I had a coded message to myself that I don't remember anymore. But no, it's from the pagination of the book. Okay. So in this simple theory, you just get unbounded growth predicted for this potential vorticity. And the picture is like this, and I tried to draw this here. Whenever you have a force field that is sort of compactly supported, if you put this down sort of in the horizontal plane, it will create a positive counterclockwise vorticity patch up here and a negative clockwise vorticity patch below, and that's how it will spin up a vortex dipole if you put down a localized force. And exactly like this is what happens here in 3 dimensions, except that you have to imagine the blackboard being a stratification surface of constant density, and then you get these potential vorticity structures spun up, and there is a secular growth, and this is a strong interaction. So with the steady wave field, you can project onto the steady linear response of this mean field system, which is in this potential vorticity controlled mode. And this is as far as we've got at the moment. So the three-dimensional simulations, we are working on those to be able to compute the horizontal structure of these effective force distributions. And then the interesting bit for the practical oceanography is that these tides, of course, go on all the time, and they have been going on since time immemorial. So there's a lot of time for effects to grow. So this forcing, if it goes on all the time, it will have to saturate sort of on the level of the nonlinearity governing the potential vorticity evolution by itself, because there isn't really anything else there. So we'll be interested to see what the strengths of the actual potential vorticity forcing is that we get out of these tides coming off the rough topography. So this is a story that we have so far, and that's it. Thank you very much.